Okay, one more video in our Chapter 3 Aerobic Metabolism lecture. This is part 4, so let's get started. Okay, with part 4, we're going to finish up talking about metabolic recovery post-exercise, something called RER, which is the respiratory exchange ratio, and then calorimetry. All right, so first, metabolic recovery post-exercise. We're going to understand the different phases that the body goes through from the start of exercise to the end of exercise, and then what happens post-exercise during our recovery. We look at this picture right here, and regardless if you have run track or not, you have experienced this feeling after a really hard workout. You've experienced this. We've all been there, I'm sure. So let's get started scientifically. What's happening to the body during our metabolic recovery? So first thing we want to look at here is something called oxygen deficit. This actually occurs at the beginning of exercise. So we read the definition of oxygen deficit, and we see that it's the delay in oxygen uptake at the beginning of exercise. We already know that oxygen uptake is VO2, volume of oxygen consumed, which is the measure of a person's ability to take in oxygen via the respiratory system and deliver it to working muscle, and the ability of that muscle to actually use the oxygen. So why is there a delay at the beginning of exercise in our ability to uptake oxygen? It's due to the initial energy production, or the ATP production, being met anaerobically rather than aerobically. We know that anaerobic sources used to produce energy to perform exercise occur before aerobic sources. We know that the phosphagen system and glycolysis are anaerobic, and they give the most energy during the beginning of exercise. It takes 2 to 3 minutes, we already know, to start producing ATP aerobically. So that's where this oxygen deficit is. This right here is the definition from the book for oxygen deficit, which is the difference between the amount of oxygen that we're consuming during exercise and what would have been consumed if we met oxygen, if our demands were met aerobically. So it's just the lack in oxygen during the initial phases of exercise. All right, so let's talk about oxygen deficit more practically. So what I want you to do is think of the last time you started exercising, and in that first minute or so, your body kind of starts to consume oxygen, but it's not efficient. So if you notice, the first minute of exercise is actually the hardest because your body is trying to catch up with what you're actually doing. So your lungs, your muscles, everything's trying to get oxygen and get energy for that movement that you're doing. So at the beginning, regardless of the intensity of your exercise, you're going to experience a rapid increase in oxygen uptake at the start, but it is dependent on your intensity. The magnitude of the slope is dependent on how hard you're working. So we see here, easy exercise, we follow that green. There's just a small, rapid increase in oxygen consumption before we hit something called steady state, which are all these flat lines, which we'll talk about on the next slide. And then you see the harder that the body starts to work, the harder the intensity, the greater the oxygen consumption, and the greater the slope at the very beginning of exercise. So easy to moderate exercise with that 1 minute lag in oxygen consumption. But when we see that severe to maximal exercise, there's about a 2 to 3 minute lag in oxygen consumption. So we have greater oxygen deficit with higher intensities of work. So there's a greater deficit when we're working harder and longer it takes to reach steady state. So the next slide discusses what is steady state. But if you look here, we're about to discuss these flat lines that you see right here. That's described as steady state. So it's when all of the energy needs are now met aerobically. So it occurs after oxygen deficit when energy production equals energy required for the exercise to continue in duration. So ATP production equals ATP needed. So there's a balance. There's a balance between ATP needed by the body and the ATP that's being produced. So we're at a steady state exercise. It's also described as the point at which VO2 plateaus. So we already know what VO2 max is. It's when we're exercising at extremely hard workloads. This shows here when VO2 max plateaus off. So when we see exercise intensity start to increase rapidly and rapidly and rapidly, our VO2 starts to increase. And this is considered that maximal exercise when we'll start to see that plateau. This also occurs at moderate workloads as well. Let's talk about the time required to reach steady state and what is it influenced by. So number one, it's influenced by the magnitude of the increase in intensity. So how hard we're actually working, and that was described on the last slide. And it is influenced by training status. And so this picture here shows trained versus untrained. So in these minutes here, we are at rest, and then the 0 is the start of exercise. And then this shows that it takes about, well, let's first look at the untrained. So for the untrained, we kind of follow the darker blue and then all the way up to about here. That's about 3 minutes for the untrained person to reach steady state. And that's saying 3 minutes until basically ATP is being produced aerobically. Untrained are less efficient in their ATP production, so that's one reason why it takes longer for untrained to reach steady state. And you see here now VO2 has plateaued. Oxygen or ATP needs are being met aerobically. And then we see the trained person, and we see there is still a very slight rapid uptake in oxygen, but they actually reach steady state in less than 2 minutes. By about 1 minute or so, 1 to 2 minutes, they have reached steady state, meaning that their ATP is now being met mostly aerobically. This basically just says that the trained person is more efficient in their ATP production and their energy systems are more efficient at producing energy. All right, so that's what happens at the start of exercise. We have oxygen deficit, and then we move to steady state. Now let's talk about, what about post-exercise? So post-exercise, once we get done with our exercise, what happens? So you probably know this if you exercise regularly, that even when you've stopped your workout, your heart rate is still elevated. You're still breathing heavy. You may be even breathing heavier than you were during your actual workout. And then BMR, that's basal metabolic rate. That's how much energy you're burning. That's also still elevated, even though you're already finished. All of this is to enable recovery and help the body recover. What is this called? Excess post-exercise oxygen consumption. I'll call it EPOC. So the rest of this lecture, I'll refer to this as EPOC. It's when oxygen consumption or oxygen is consumed above resting values after exercise. So it's when you're consuming more oxygen to help the body recover, even though you're already done with your workout. This is basically to help restore the body to its pre-exercise condition, and it actually represents the energy borrowed from anaerobic sources to perform the exercise at the beginning of the workout. So intensity versus duration on EPOC. So let me give you an example. Is my EPOC going to be higher after, let's say, I run for 6 miles at a moderate pace versus if I do 10 repeat let's say 60-meter sprints back to back? My EPOC is going to be higher after a sprint workout than it will be after a slow, long duration endurance workout. So what I want you to note here is intensity of the workout has a greater impact on EPOC due to increase in lactate and increase in acidity during the higher intensities. We require more oxygen to aerobically metabolize and clear acidity. So oxygen helps to clear away lactate and acidity. And so when lactate and acidity is higher, we're going to be consuming more oxygen. So meaning we're going to be breathing harder even though the exercise has stopped. Also, the elevated temperature with high intensity exercise requires more oxygen to help decrease that temperature. Low intensity, long duration runs performed at steady state has a lower impact on EPOC. So yes, you will still be breathing heavy after you get done with, a 4, 6, 10 mile jog. But that EPOC, that really heavy breathing after exercise is highest with really high intensities, like a HIIT workout or really heavy resistance training bouts or sprints. So here, recovery is needed to perform repeated anaerobic bouts. So this is kind of referring to like a HIIT workout or like repeat sprints. So we need an aerobic recovery period in order to perform another bout of high intensity. And this was discussed in chapter 2, but that recovery period is necessary to resynthesize creatine phosphate. Once we start aerobically recovering, creatine phosphate resynthesis starts to occur immediately. And then after about 2 to 5, 3 to 8 minutes of rest, our ATP and creatine phosphate will be recovered. And then we also need a recovery period to decrease lactate and acidity before we do another sprint or do another workout or a resistance training workout. Because lactate is about 70% aerobically metabolized, meaning we combine it with oxygen and it goes through other oxidizing reactions, which we can breathe it out as CO2. 20% of our lactate is cleared to make more glucose in the Cori cycle or the lactate shuttle. And then 10% is used to synthesize amino acids, so for protein synthesis. So we need to clear lactate and we need to restore creatine phosphate and ATP. So that's why that recovery period is needed. So there are 2 phases of EPOC. First is the rapid component. So here, let's start at the very beginning, resting oxygen consumption, start of exercise. We have oxygen deficit, which we already described, and then here we have reached steady state to where all our ATP needs are being produced aerobically. And then here we end our exercise, and then there's an EPOC rapid phase. So this is where most of the ATP and creatine phosphate is resynthesized in about 2 to 3 minutes. And then down here is the slow phase of EPOC recovery. So this is when the heart rate, breathing rate start to return to resting values. This takes greater than 3 minutes. Also, rate of recovery is influenced by training. So trained individuals have lower EPOC, meaning they're not going to be breathing as heavy once they stop their exercise, and they have faster recovery. This is something called parasympathetic tone. It means that they can restore or they can get back to or have that parasympathetic activity come in quicker than the untrained person does. We'll learn more about that in chapter 6 when we start to talk about the cardiovascular system, and then also a little bit in chapter 5 when we talk about the peripheral nervous system and that parasympathetic. But increased parasympathetic tone is recovering quicker, where we can decrease our vitals, so restoring vitals, establishing baseline homeostasis, kind of returning our hormones back to normal concentrations. There's also something called the afterburn effect. So what is this effect here? So it's basically when EPOC will increase energy expenditure post-exercise, so the afterburn. Every 1 liter of oxygen consumed will burn 5 calories post-exercise. So that's roughly about 50 to 200 extra calories are burned by EPOC after intense bouts of exercise. So exercise where we reach 70 to 85% maximal heart rate and mostly anaerobic exercise. So we burn about 5 calories per 1 liter of oxygen consumed post-exercise. There was a study that looked at participants who cycled vigorously for 45 minutes. They burned roughly 190 calories in the 14 hours after exercise compared to the days that they did not do a workout. So yeah, that afterburn effect means you'll continue to expend energy throughout the rest of the day after a really hard bout of anaerobic work. All right, let's put it all together and wrap up this topic here. So oxygen deficit and EPOC and steady state. So first here, we've started exercise. So once we start exercise, we'll have a rapid increase in oxygen, and there will be a delay in the oxygen that the body needs to perform the exercise due to our ATP being met anaerobically. But eventually, we'll reach steady state here. And so steady state, now we have our oxygen needs are being met and our ATP is equal to what's needed by the body. And then we'll stop our exercise and we'll go into EPOC, the rapid component where we resynthesize ATP and creatine phosphate, and then the slow component where we restore our vitals, heart rate, breathing rate, and temperature. So the magnitude of the oxygen deficit and the EPOC, we probably already know is determined by intensity, not duration. So the intensity of our workout has a greater influence on oxygen deficit and EPOC post-exercise. Another statement is so oxygen deficit and EPOC, both of those, there's greater oxygen consumed than during steady state. So more oxygen consumed at the beginning and the end of the workout rather than in the middle, which is pretty interesting. This YouTube video here talks about EPOC and recovery, so watch that if you're interested. Okay, so let's continue talking about recovery and how to maximize recovery. There are two ways that we can recover post-exercise. First is passive recovery, where there's no physical activity done during the recovery period. So this is basically when you finish your workout and you immediately just sit down or stand with no movement. So you do lots of sprints or you complete a cycling race and then you just immediately sit down and there's no more physical activity. Versus active recovery, which is where there's light to moderate aerobic exercise post or during that recovery period. So an example of active recovery, let's say, would be cycling at about 30 to 45% VO2 max. This would reflect more localized muscle involvement and lowers intensity in which lactate threshold would occur in the quads. And then jogging, let's say at like 50 to 65% VO2 max. This is another example of active recovery. This is, or the intensity must be below lactate threshold, or blood lactate will start to increase again. So it really does have to be on that really light, maybe a little moderate side, or lactate will start to increase and then we're actually not recovering. And then let's talk about why does this allow decreased lactate faster. So due to aerobic metabolism of lactate to produce ATP to meet energy demand of the working muscle at light to moderate intensity, lactate will decrease. So lactates decrease faster because we are taking lactate and we're turning it into glucose to make more ATP. Active recovery will also help to maintain blood circulation, so allowing blood to continue to circulate and helping to clear away acidity. If we look at this picture down here, we see that after a workout, we have passive versus active and what happens to lactate. So lactate will still increase post-exercise, and then once we start our passive or active recovery, you can see that active recovery will decrease lactate levels faster, but even after the 50 minutes of recovery post-exercise, regardless of if you did passive or active, you're back down to baseline lactate levels. All right, so let's move on to a topic called respiratory exchange ratio. So we can see here that respiratory exchange ratio is the ratio of oxygen used and CO2 produced during exercise or during macronutrient metabolism. It describes the oxygen needed to metabolize carbohydrates and fats and the amount of CO2 produced during that process. It's expressed in a ratio depending on which substrate is most metabolized. So, RER is going to be between 0.7 and 1, and that's the ratio. Basically, that explains there's a mix of carbs and fats being used. It has been shown to exceed 1 at extremely high intensities and short durations, but this is less accurate during anaerobic metabolism and more accurate during aerobic. Respiratory exchange ratio is also most accurate during steady state exercise. So we see at rest up there, we see 0.8. So that basically gives us that percentage, those percentages that we learned earlier in the chapter. About 33% of carbs and 66% of fat is being metabolized at rest. So that's the ratio, this 0.8 ratio. It also, and then maximal intensity, RER is going to be 1. And we know this already. That just means 100% carbs are being used during that maximal intensity. So gives us a ratio of 1. RER does not take into account protein. So protein is not calculated kind of in this ratio because carbs and fats are going to be the primary energy source that's used during rest and exercise up to maximal. What do you think the effect of aerobic training is on RER? So comparing a aerobically trained individual to an untrained individual, what would you guess? Trained individuals basically can train the body to rely more on fat for aerobic exercise, which we learned in the last video is called glycogen sparing. And if they're relying more on fat, they're going to have a lower respiratory exchange ratio. So it's going to be less than 1. It's going to be somewhere in between 0.8 and 1. That'll be the RER based on their ability to spare glycogen and turn to their fat stores. So here is a chart that looks at RER estimates of percentage of carbs and fats metabolized and the calories produced. So what I mainly want you to look at here is the 0.8, which we know is rest. So 33% carbs, 63% fat, that's rest. When we are at the body's at rest, that's the RER. And then the other number I'm concerned with you knowing is maximal intensity is 100% carbohydrates, 0% fats, and that RER is 1. I mentioned earlier the afterburn effect basically says that per liter of oxygen consumed, we burn about 5 calories. And you can see that here, that also occurs during exercise. But it varies from 4.6 or, if we're at rest, 4.8 to 5.05, which is roughly the same as just burning or expending 5 calories. So we burn 5 calories per liter of oxygen consumed, and it's slightly different from rest to maximal intensity. All right, so moving on, this slide here will talk about the difference between indirect and direct calorimetry. So first, let's talk about indirect, which is this picture right here. So indirect calorimetry is first, it is more convenient than direct, and it's less expensive. It's more practical to see this performed in a lab, and it's easy to do and easy to get values by. And it's performed in our department, so our exercise physiology professors do this, and this is called a metabolic cart. So this metabolic cart right here, you can see it's hooked up to him and he is breathing in and out while he's running on a treadmill. What this metabolic cart here is doing, it's measuring the oxygen he's consuming and the CO2 that he's producing and the volume of air that he's ventilating during his exercise. So this will indirectly calculate his metabolic rate. So it's an overall estimate of metabolic rate, which is how much energy you're expending during exercise, determined by oxygen consumed and CO2 produced and how much air you're ventilating. This makes sense because if we look at the last slide here, we see that depending on our intensity, we're burning about 5 calories per liter of oxygen consumed. So if we can measure oxygen consumed in liters, so the volume of air that we're ventilating, we can determine energy expenditure during exercise. Again, that's an indirect assessment. Here is direct calorimetry. So this is our direct measurement of energy production. This is our most accurate way to assess energy use or metabolic rate. So let's start with just by discussing that all metabolic processes result in heat production and required energy to perform those cellular processes that we've learned about. So metabolic rate is proportional to the heat that we produce. And you can see in this picture, heat is being produced during the movement or during the cycling that he's doing. So this here is an airtight chamber surrounded by a water jacket. The exercising person will put off heat, which will increase the temperature of this water. This allows for calculation of energy expenditure. Normally I would ask in class, how does this calculate energy expenditure? So one thing you have to know, a calorie is actually, the definition of a calorie is a very small amount of heat, and it's defined as heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So that's kind of what this is measuring. It takes the initial temperature of the water and then how much heat this person puts off. That will determine how much the temperature of the water has increased, and we can measure energy production that way, or calories expended. You can also see that here's the airflow in that he's breathing in, and then the airflow out, basically so he's getting oxygen supply, and then we're absorbing that CO2. So yeah, we can measure all of that, and that's a direct assessment. But this is rarely done in labs, especially in this department and most other departments. So this video here will look at a VO2 max test and how we can measure energy expenditure.
The VO2 max test is a test to determine your body's maximal consumption of oxygen and the efficiency of your muscles. To do this test, our goal is to get you to max exercise to determine your heart rate max, your VO2 max, and an estimated lactate threshold. During the test, we're measuring oxygen consumption and CO2 production to determine all these values. And from that, you can help set your heart rate training zones. The best way to use this is as a change over time measure to determine how your workout plan is going, if you're getting better, whether that's running, CrossFit, any sort of cardio-based exercise. The protocol for this test is we choose a speed where you're comfortable but not too comfortable, and every minute we're going to increase the incline on the treadmill. Our goal is to max you out in about 10 minutes so that you're not running at too high of an incline and your oxygen consumption gets to that full max along with your heart rate max. During the test, we're graphing the heart rate, so your body's response to the increases in exercise intensity, along with your VO2 relative to your body weight, and the liters per minute, your ventilation during the test. Here we're measuring a variety of variables. The graphs here are showing the heart rate throughout the test, and then this is the VO2, so your oxygen consumption relative to your body weight, and then your ventilation, so how many liters of oxygen and airflow you're moving per minute. I'm Kimberly Gandler. Thanks for watching.
All right, so that kind of gives you an example of the indirect calorimetry. So let's move on, but we're still kind of been talking about basal metabolic rate, which we know is energy production. So basically how much energy the body is producing and calories expending. So energy expenditure. So basal metabolic rate let's kind of look at this definition. So metabolic rate taken in a supine position, meaning laying on your back, 12 to 8 hours after a meal. So basically waking up in the morning and getting this test done. So immediately after waking up in a thermoneutral environment. This accounts for about 60 to 75% of total calories expended during the day. This is actually done in Dr. Grant Tinsley's lab in our department. It's a very accurate assessment, but kind of inconvenient. I've done it before. You have to lay down with like a big bubble over your head, and it just measures your oxygen consumption, CO2 production, and that can get an assessment of how much energy you expend during the day, but it's at a rested state. So if you were just to lay in bed all day and not do any movement, how many calories do you actually expend during that time? This only accounts for 60 to 75%. My question for y'all is, what do you think accounts for the other percentages? And that's going to be physical activity, and then TEF, which is the thermal effect of food. So when we consume food, our body expends energy breaking down that food and digesting it. And so it puts off energy. We expend calories when we digest food, but not a lot, just a small percentage, like 10% or 15% maybe. And then the other percent is the exercise that we do. So about 25 or so percent exercise we do during the day that also contributes to our energy expenditure. Resting metabolic rate is similar, but this is 4 hours after a light meal with 30 to 60 minutes of resting quietly. So laying down, resting quietly, just 4 hours after you've consumed a meal. This has easier guidelines to follow and account for, and it's not as accurate as basal metabolic rate, but it still gives you how much energy you expend at a rested state. So a question here is, what factors influence RMR? So resting metabolic rate. Normally I would have y'all discuss, I have about 6 factors on my slide. I would have y'all talk to each other, come up with answers for this. But number 1 is age. So we'll see a decrease in RMR due to a decrease in fat-free mass or muscle mass. So as we age, as we get older, we expend less calories because our body, we start to lose muscle tissue after age 30, and then so on and so on as we get older. And the more muscle mass you have, you burn more energy. So you expend more energy with more muscle. And if we lose muscle with age, then our RMR would decrease. Oh, sorry. Next is sex. Males have an increase in RMR due to greater size, so greater body size, and decrease in body fat. So males expend more energy than females. That's probably well known by most. But the reason is greater size. So larger body size expends more energy. And then also, the less fat you have and the more muscle tissue you have, you expend more energy. I keep doing that, sorry. Another one is stress. So due to an increase in sympathetic activity and adrenaline, like epinephrine and norepinephrine, we're going to see increase in energy expenditure. So anytime you're stressed or have a lot of adrenaline, your body expends more. Another one is temperature. So higher temperatures with exercise and with illness, you burn more energy. And then last is surface area. So those with a larger body have a greater surface area. And if there's more surface area, there's more available heat loss. So there's more heat loss. The larger the surface area, the greater the body. But yeah, those are the factors. So you can watch this video down here at the bottom, and it goes over metabolic rate testing, and it gives you kind of an example. It shows a video of someone getting this test done and what the benefit and use of it is. So yeah, you can watch that video at the bottom. But that is it for this chapter. Well, I hope you enjoyed it. And now you can complete your Chapter 3 assignment and your Chapter 3 quiz. So look in the syllabus for the due dates for each of those. But let me know if you have any questions. Reach out to me. I'm here. But other than that, I will see you in the next